All right, so today we're going to start on composition and combinations of functions, and then we're going to end with the difference quotient. And the difference quotient is something we like to expose you to in pre-calc if we can, because it is a huge, huge part of Calc 1. You will spend quite a lot of time at the beginning of the semester in Calc 1 working with the difference quotient, and it actually has a purpose in calculus that sort of all of Calc 1 is based on. So one of the things about the difference quotient that can be kind of tricky is the algebra. And so it's nice to kind of get to see how to do it. It actually does go with what we're doing today and kind of get a leg up on how to do the algebra. But conceptually, when people get into calculus, it's not really the calculus that's the problem for them. It's if you don't have a good underlying background of algebra, it can, get in your way. So today what we're going to talk about is, first, we're going to talk about combinations of functions and go over all the kind of algebraic rules and, more importantly, the notation, because there's a couple different ways that the notation can be written, and I want to make sure you guys understand how to read that properly. So we can combine multiple functions into new functions that we can work with. So when you see something like a polynomial, for example, right, like x squared plus 2x plus 3, right, that's really a way of thinking about that is a combination of three individual functions, x squared, 3x, and 3, and they were added together. So you need to make sure you understand kind of the do's and don'ts of combining functions. So just like when we work with arithmetic and we kind of have the four major operations, right, addition, subtraction, multiplication, and division, we can actually do those same four things when we're combining equations together. So if you have two functions, f of x and g of x, okay, we can do lots of operations to combine those functions together. God, it's 75. Terrible. Okay. So we can add those two functions together, right? And one way you'll see that notation, right, is something like this. You could see f plus g of x, and that is the exact same thing as saying take f of x and add it to g of x. So if we want to, we're actually going to do an example with all of these in a minute, right? We can also subtract functions from each other. So if you see f minus g of x, that is the same thing as saying f of x minus g of x. We can multiply two functions together. So sometimes it's shortcutted, and people write fg of x, and that is the same thing as saying f of x times g of x. So you'll notice that some books and homework people prefer the stuff on the left. Personally, I prefer the stuff on the right, and so usually if I see the notation on the left, I will translate it into the stuff on the right and then proceed with the problem, because this is giving you, in my opinion, a little bit better instructions on what to do. So then similarly, right, we can say, well, f divided by g of x is f of x divided by g of x. So if we look at these four operations, what I want to do is I want to look at two functions, right? We're going to let f of x be the square root of x and g of x be x plus 5. So f of x is, right, the square root of x. It has a domain, right, of any value greater than or equal to 0, right, because of this radical. The radical says no negatives underneath it. So the domain of f of x, right, is going to be 0 to infinity. And if you can kind of visualize the base graph of this, it was on the worksheet I gave you guys. Well, the square root of 0 is 0, right? And as you plug in bigger and bigger positive numbers, the square roots are going to go up, right? So the range of this function is also 0 to infinity. What type of function is g of x? Linear, right? It's a line, right? So you just look at the power, the highest exponent of x, right? It's a 1, so it's a line. It's also in the form of mx plus b, right? It's a line with a slope of 1 and a y-intercept of 5. So lines, right, have domains of all reals and ranges, right, of all reals. So everybody can kind of visualize a line in your head, and all lines, right, unless we put some kind of application restriction because of the context of the line, are all reals, all reals. Furthermore, if you looked at that, right, and you're looking at the domain, right, there's no radicals, there are no denominators, and there are no logs. So there's no like major restrictions to check for. So every number of x can go in, right? So what I want to show you is that when you combine functions, right, you can't just look at the original domain and range of the functions when you combine them to find the new domain and range. You have to combine them, look at the structure of the final equation, and then you may have to adjust the domain and range slightly. So if we want to add these two functions together, if I want to know what f of x plus g of x looks like, well then I'm simply going to take the first function, right, and add the second to it. So the parentheses are not necessary. I'm just putting them there so you can see the first function plus the second function, okay? So if you look at this new function we've created, well, what do you think the domain of the new function is? What's not allowed? Let's go there. Negatives, right? So even though the line will take everything, right, that square root at the beginning now knocks all negative values from the function. So if something like this appears anywhere in the equation, even though the x by itself would typically accept it, it has to be true for all x's, because when you evaluate this new function, right, we can name it h of x if we wanted, you plug in the same value for x everywhere in the equation. So the square root now knocks all the negatives away, so the domain of this guy is now 0 to infinity. 0 is okay because the square root's in the numerator. So similarly, if we were to subtract these two functions, and this is where you want to be really careful. So you can't just write square root of x minus x plus 5. That's not going to work, right? You're subtracting the entire function g of x. So here the parentheses are necessary because I have to make sure that I'm subtracting the entire expression. So that negative sign has to get distributed across the whole thing. So if we take our -1 here and distribute it across, the new resulting function is actually square root of x minus 5. If we had done this the other way, right, you would have gotten away without using parentheses because you had one term you were subtracting. But you always want to make sure when you're subtracting that you're doing the entire expression. And you'll see when we look at the difference quotient later, the numerator is always the difference of two things, and that is parentheses are your best friend there. Right? So here we have the exact same domain that we had up here, right? These guys will accept any value of x, but this guy is still not going to allow anything negative to be plugged in. So the domain of this is still 0 to infinity. All right. Well, if we want to multiply our two functions together, well, then I'm simply going to take the first function and multiply it by the second. Once again, you need parentheses here because you have to make sure the entire expression is being multiplied by the first. So we could leave it like this. If we wanted to expand this out, we can say x square root of x, right, plus 5 root x. And another way we could write this, if we didn't want to have the radicals and the x's combined, well, that first term is x to the 1, right? Square root of x is x to the 1/2. So you can actually add their exponents together because they have the same base. and this would also be an equivalent answer. Okay, so one of the things you have to be careful of is if you see the expression given with fractional exponents and I ask you to find the domain, right, it's the denominator of the exponent that's telling you whether it's an odd or an even root. The fraction bar implies radical, okay? So you would have to know that there's a domain restriction here because we have a square root, right? And it's easy to see the square roots here and here, but it's not so obvious when you see it written like that. So once again, this thing will not allow the radicals in our way. The domain of this function is going to be 0, right, to infinity again.
Wait, why is it 3 halves and 1 half?
Because this is, so x root x is the same thing as x to the 1 times x to the 1/2. And when you have the same base, you add the exponents together, right? So like x squared times x cubed is x to the 5th. You add the exponents together. So you can do the same thing with fractional exponents as well. That's just the rule of exponents, as long as they're the base. And when you get into calculus and you work with radicals, you're actually going to find that working with fractional exponents is much, much easier for a lot of the things you're going to do than actually writing out the radical. Because a lot of people, if they had to do algebra, wouldn't always know what to do with this, right? But we can combine it into one term, right? And so the last operation that I want to look at is dividing them, right? But I want to look at this 2 different ways, okay? So if we look at the first way, let's put f of x in the numerator and g of x in the denominator. So f of x was the square root of x, and g of x was x plus 5. Well, here I have 2 potential domain restrictions to have to deal with. I have a radical that I have to make sure no negatives get plugged into, but I also have a denominator that won't allow the denominator to be 0. So what value of x would make the denominator 0? -5, right? But what values of x are not allowed in the numerator? Any negatives at all. So even though -5 doesn't work in the denominator, the numerator won't take it anyway. It won't take anything. So the domain of this is still going to be 0 to positive infinity. So yes, -5 won't work, but the numerator won't take it either. And as a matter of fact, the numerator won't take -1, -2, anything negative. So that would be the domain, right? If we flip it the other way, and we divide g of x by f of x. Well, now you have x plus 5 on top, and you have the square root of x in the denominator. So now the numerator's fine. And the numerator can be 0 all day, so it doesn't matter. The numerator will take all real values of x, right? But the denominator now has 2 rules that kick in. You can't plug any negatives into the radical, but now you can't plug 0 into that radical either, because that would give you 0 in the denominator. So, right? Everybody see that? So the domain here, instead of including 0, we would say 0 not included to infinity. So remember that those restrictions that we gave you, right, can be used in combination. So you can always have 0, square root of 0 in the numerator, but you cannot have the square root of 0 in the denominator. All right, any questions about this? Okay. So the other thing we can do with functions is we can do what we call compose them, okay? So a composition is simply plugging one function into another. And this is a little bit different. And because we said that functions can be expressed in 3 different ways, they can be equations, right? They can be tables, and they can be graphs. There's 3 different kind of techniques you need to do when you're composing functions depending on how the function was presented. So we're going to look at equations first, and then we're going to look at tables, and then we're going to look at graphs, okay? So in this particular operation, the algebra is actually the easiest way to do it, I think. And then the visual way is actually the more difficult way because you have to be a lot more careful with how you do it. So if we just stick with our, well, let's look at the notation first, right? So if you see f in this little circle of g of x, that is the same thing, right, as f of g of x. So you read them in order from left to right. And what you're doing here, that little O, right, is just read of. F of G, and some people think it looks like fog, right? But it's just F of G of X. So when you read it on the right, you can see the parentheses are read as of, so F of G of X, right? If you want to evaluate F of G of X, right, when we evaluate a function at a value, we plug the X value in and then simplify it and work out. This is kind of like a fancy dinner party in reverse, right? Everybody tells you if you ever go to a fancy dinner party and there's lots of cutlery out on the table and you don't know what, they always say to work from the outside in, right? Compositions are the opposite. You work from the inside out. So you will always go to the what's absolutely in the middle, right? You'd evaluate G of X first. The Y value that comes out of G of X is now the X value you would plug into F of X. And so we can actually compose more than just two functions. I could have had F of G of H of X, right? And you would have done H of X first, then G of X, then work your way out to F of X. So, and that's why it gets tricky when you have to do it visually, because you have to, your Y's and X's can get kind of confusing, right? Similarly, if you see, right, G of F of X, well, that reverses the order. So that's now saying plug F of X into G of X. So if we're working with our same two functions we had before, right, F of X was the square root of X, G of X was X plus 5, and I want to find F of G of X. So if I want F of G of X, what's going to happen is the entire expression from G of X, which was X plus 5, gets plugged into every X that exists in F of X. So I would say, well, F of X is the square root of X, but instead of just writing X, I have to write all of G of X. So this would become the square root of X plus 5. If I want to find the domain of this function, well, we still can't have negatives under the radical, but I'm not just talking about just one X anymore, right? I have an expression. So what we're saying now is the entire expression X plus 5 must be greater than or equal to 0. And the reason we have to include 0 is this radical's in the numerator and it's allowed to equal 0, okay? So now we would just solve this for X and we would say, well, then X has to be greater than or equal to negative 5. And so there's kind of two ways of doing this. We can graphically, right, sketch the domain. And this says keep negative 5 and only accept values of X that are greater.
How do we keep negative 5 if it's...
Because of the equal to sign. You're allowed to have 0 inside of a radical as long as that radical is in the numerator.
Okay.
Square root of 0 is 0. Right? So if you plug negative 5 in, you're just going to get square root of 0, 0, right? If I did 1 over square root of X plus 5, we'd have to throw negative 5 out. Yep. So the domain here is negative 5 included to positive infinity. And so like we said before, right, all you're doing when you're checking for domain of an equation is you're checking for the values of X that are not allowed, and then you get to assume all the other ones are okay. And there's just kind of those three checks we look for, right? So if we want to compose this the other way, if I want to say find G of F of X, well now I'm going to go to G of X, and everywhere I see of X, I'm going to plug in the entire expression for F of X. So G of X was X plus 5. So this x right here gets replaced with f of x. So this is the square root of x plus 5. So does anybody want to take a stab at what the domain of this guy is going to be? Zero included or not included?
Included.
Included.
Yeah.
It can be in the radical. Yep. So the only thing in our way in this one is that square root of x. And as long as it's 0 to positive infinity, totally allowed, right? So one of the things I wanted you to see about this is if you go back and look at all the domains from all the different things we did to these functions, they varied, right, based on the structure of the resulting equation. So sometimes we got to keep things, sometimes we had to throw stuff out, right? So there's one other thing that you have to be careful for, and we'll actually see this more clearly in a second when we look at a table. But when you're composing functions, right? If values in the range of g of x, okay? So here's what we're saying here. If you wanted to actually evaluate this at specific values of x, right? Well, we would plug that value into g. The y value that comes out of g, right, becomes then the input variable, right, into the next function. So if the values of the range of g, right, the y values that come out, are not in the domain of f, right? So let's say we threw a number into that line, right, and we got a negative number out, right? Let's say we're using our original two functions. So I plug -6 into g of x, so it came out as -1, right? Well, then I'm supposed to plug -1 into f of x. But I can't plug -1 into f of x because f of x was the square root of x, and you can't plug a negative into there. So if the values in the range of g of x, sorry, got a little early with the comma, are not in the domain of f of x, we may need to restrict the domain, okay? So with equations, we were sort of doing that implicitly already. We were looking at the structure of the final equation, and it was kind of telling us what we could do and what we couldn't do, okay? But when you're looking at tables and graphs, you may have to manually adjust the domain accordingly. So let's look at two functions that are given as tables and see what we're talking about here. So now we have, these are definitely functions, right? None of the x values are repeated. We have two different functions, but we're only given the information as tables. And so what essentially you have are just 4 points. If you graph it, that's all you're going to see is 4 dots on each graph. We can't connect the dots because we don't know anything about anything going on in between. So if you want to know what f of 1 is, right? You go to the f of x table, right? You find x equals 1 and the y value is 5, right? If we want to know what f of 3 is, the y value is 6, okay? Similarly, if you want to know what g of 6 is, right? The y value is 11. You just go to the top row, find the corresponding y value. But when you want to compose functions using tables, it can get a little bit tricky. So let's say I want to know what g of f of 1 is. All right? So this is where you got to kind of work from the inside out. So the first thing is we need to find the value of f of 1. So if I go to the table, f of 1 is 5. So that means I replace f of 1 with the value 5, with the corresponding y value. Now I have to plug 5 into g of x. So I have to jump over to the g of x table, and here's where x equals 5, and we can see that the value comes out as 10. So this is what I mean by working from the inside out, right? F of 1 equaled 5. We just literally replaced it in the equation, right? What happens if we want to find, right, g of f of 3? So for g of f of 3, well, f of 3 is 6, so that's really saying find g of 6. And if I go over to the g of x table, g of 6 is 11. Right? And once again, right, we just replaced f of 3 with 6. Okay? But look what happens if we try to find this. We try to find f of g of 1. Okay? So if we're supposed to work from the inside out, well, if you go over to the g of x table, right, there is no 1 in the x column. 1 is undefined. So if you can't produce a y value, then you have nothing to plug into f of x. And so this is undefined. All right, but if we want to find f of g of 6, right, we can go over and we see that f of, right, g of 6 is 11, right, so we do get a y value out. So now it's saying, well, find f of 11. Well, when you go back over to the f of x table, there is no x value for 11. So this is also going to be undefined. So these compositions are a two-step process, right? You have to find the first value, then you have to use that value in the second. So both of these equations failed, but they failed at different steps of the process. This wouldn't even let you get past step 1. It was like, nope, doesn't exist, we're done, right? This let you did get past step 1, but then failed at step 2. So there's multiple ways something can be expressed as being undefined. So let's look at the domain of these functions. So clearly, right, if I want to express the domain of f of x, we said when you have tables, right, you're just reporting back a set of values. It's just a list. And we don't usually repeat numbers. So the domain of f is just going to be 5, 6, and 8. Even though 5 appears twice, we only have to list it once. Okay? And so all I did was look at the y values that come out of the function, because that's the range. I'm sorry, did I say domain? This is the range of x. All right? The domain of f of x are the x values. So 0, 1, 2, 3. Yeah, someone looked at me like I had 2 heads. All right. The domain of g of x by itself is 5, 6, 7, and 8. Right? It's just those are all the values that are allowed to be plugged in. But what is the domain of f of g of x? All right, and this one's a little bit trickier. So the domain of f of g of x are only the values of x that are going to produce, that are going to make it through both steps of this process, right? They're going to actually let you complete the equation. So if we look at g of x, we start from the inside out, right? And I just want to grab the x values that are going to actually let me plug into f of x and give me a final answer, right? So 5, right, produces 10. 10's not up here, right? 11 is not up there. 5 is not up there, but 3 is up there, right? And so what did that definition say when we started with this, right? We said if the values in the range of g of x, so the range is here, right? If those values are not in the domain here, right, you're not going to get a final answer. So all I'm doing with the table is I scan the y values of the inside function and make sure they have corresponding values on the top row of the outside function. So you look at the range here and compare it to the domain here. And the only value that's here and here is 3. So we see that? So that's the only thing that's going to actually produce a final result for you. So the domain of f of g of x is just 3. Oh, my bad. 8. Screwed up. Why is it 8 and not 3? Because it's the x value, right? It's the original x that produced that. So 8 maps to 3, and then 3 would map to 6. So as a matter of fact, the range of this function, this is the domain, the range is the y value that comes out at the very end, and that number would be 6, right? 3 is just sort of the intermediary step that connects the two, okay? So let's look at g of f of x. So for g of f of x, right, we're going to do the same process now, except now the inside function's f of x, so I'm going to scan the range and see which values work over here. So we have an 8, a 5, and a 6, and we have an 8, a 5, and a 6. So all 3 of those values are going to work out. And so I need to grab the corresponding x values. So that means 0, 1, 2, and 3 can all be plugged into here. So if I plug in 0, I would get 8, and then 8 would return 3, right? If I plug in 1 or 2, I get 5, and 5 would return 10. If I plug in 3, I get 6, and then 6 would return 11. So all the original values in the f of x function would be allowed to be plugged in. And so the domain of this is 0, 1, 2, and 3. Right? So we said, right, that the range of this guy was 6, right, because that's the only value that comes out when you plug in 8. But the range of this guy is 3, 10, and 11. So the range of the composition, right, grabbed every value in the range of g of x except for 5. Why did we not take 5?
Because it repeats.
You don't have something that gives you 7.
Right, you don't have something that gives you 7 to plug in to get that 5 back out. So notice here, this 5 repeated, right, which gave you 2 x values, 1 and 2, right, for the domain, but 5 was only in one column over here, so both of those were going to produce 10. But we had nothing that mapped to 7 to give us this 5 out of the equation. So you want to make sure that you're being really, really careful when you're doing domain and range of compositions, but that's one way you do it. You look at the range of the input, the inner function, compare it to the domain of the outer function, and if they don't line up, then you don't have a way to connect step A to step B. All right. All right, so graphically, and this is where people kind of lose their minds a little bit. All right, so we can look at 2 functions This will be our f of x. Right, then we're going to have g of x. And just to make this a little easier on us, I'm going to grab functions where we can quickly grab points, just to make this a little bit easier. So if we want to look at the composition of these two, now, normally, when you're doing this, they would not give you the equation of the graph. I'm just doing that so we can grab our points quickly. So you couldn't cheat and do this with the equations. But since I actually have the equations, I could kind of check myself by doing it algebraically. But typically what they would do is they would give you a graph and they would label a bunch of points on the graph, right? And every point's going to have an x and a y value. And so we would do this the same way we would before, but one of the things they'll do to be cruel and unusual is you're going to see a lot of the numbers repeated in the x's and the y's, so you have to be very careful that you're grabbing things from the right place, right? So you'll see lots of like 1s and 2s and 3s, and some will be y's and some will be x's, and it gets a little nutty. So what you would want to do here is if I wanted to know what f of g of 1 is, okay? Then what I would do is the inside function, right, is g. So I would come over here to the graph of g of x, and hopefully the point, right, 1, 1 would be listed for me, okay? So f of g of 1, right, g of 1 is just going to be 1. You plug in 1, 1 comes out, okay? So that's the same thing as saying find f of 1. So then on this graph, well, f of 1 is also 1, right? Plug in 1, square it, you get 1 out. So the answer here would just be 1, okay? But what about f of g of 3? So if we came over to our g of x graph, right, you would find the point when g is 3, right, the y value is also 3 because every point on the line y equals x is just x, right? So this is the same thing, right, as saying f of 3. So then on this graph, you would locate the point where x is 3, and you would see you get 0.39 because you have to square every number in x squared. So f of 3 would just be 9, right? And if we wanted to reverse the order of the composition, so let's say we want to find g of f of 5, right? Well, f of 5, right, when we find the x value that corresponds to 5, on f of x, the y values get squared, so that becomes 25. So then we would find g of 25, and on g of x, right, all the x's and y's are the same. So you find the x value on the input function, find the corresponding y value, then plug that y value into x on the other function, and find the new y. So it's the same procedure we've been doing all along, you're just going to have to do it visually, and it can get a little crazy, yeah.
So do they give us the points or no?
Yeah, usually the graph and all the points are labeled and you're just kind of jumping back and forth like you were on a table. But I just wanted to give you functions where you guys could understand where the points are coming from and how to identify them. We could just give you a graph, but it would be on a grid and you would have to like count over and go, okay, x is 1, go up, okay, this is 0.11. So sometimes they'll give you the points or sometimes they'll give it on a grid where you can actually label and find them yourself. Yeah, but you may not always be able to identify the equation of the graph you're looking at, even if you can find the points. So that's why I was like, don't always assume you can rely on algebra to get you through it. Because what I would have done, if I'd recognized the graph, I was really good at going, oh, this is x squared, this is x squared plus 2. I would just figure out what the equation is and do it algebraically. But you would just go over and say, okay, find point 1, that y value is 1. So now I got to come over here, plug that 1 in, find that corresponding was 1. Yeah. All right. So the last thing I want to look at, and we may have to finish this, we'll probably do another one of these on Monday just because these are a little tricky. The algebra, is I want to introduce the concept of the difference quotient. This is a hugely important idea. So what the difference quotient is a variation on the slope formula that we learned earlier, right? So we talked about when we learned slopes of lines, we said that it's the change in the y value over the change in the x value, right, between any two given points. And when you're doing that on a straight line, that value is constant for whatever 2 points you pick on the line. Whenever you calculate it, you're going to get the same value. However, what if we're not looking at a line, okay? What if we're looking at a curve, right? The graph has a curve in it. So we can still talk about slope. It's the same mathematical operation if you look at the change in the y values over the change in the x values. But now we don't really define it, even though it is a slope, right? We now talk about it in terms of, we say the expression, the average rate of change, right? So if I want to know what the average rate of change between these 2 points are, so I'll say this is an x value of A, this is an x value of B. The corresponding y values, right, are f of A and f of B, right? So you would plug that value into the function, and f of A would be the y value that came out, right? Whatever number you get. You plug B in, f of B would be the value that came out. If I draw a straight line here that connects these 2 points, right, this is what we call a secant line. So once again, just like with tangent lines, this isn't the trig function, right? A tangent line, right, was a line that touched a curve in exactly 1 point. A secant line is touching the curve in exactly 2 points, okay? And notice it's kind of inside the curve, right? If I slid this line, like if I took this line and just slid it up until it only touched the line in exactly 1 point, right, then that would be the tangent line. That would, the parallel line that would have the same slope, right? So if I want to calculate the slope of this line, this is what we call the average rate of change. And I'm just going to abbreviate that with ARC. So just like we did with slopes, right, there's your change in y, there's your change in x, and so the change in y is going to be f of b minus f of a. That's going to give you the height of this triangle right here. So the numerator is f of b minus f of a. The denominator is going to be the change in the x values, so you subtract their x coordinates, and here we say b minus a. Now, unlike with the slope formula, right, where we kind of said you can sort of use any point first or second as long as you're consistent, here we typically want to see the upper, right, you want to read the y-axis from top to bottom, and you want to read the x-axis from right to left, because you want to make sure you're getting these points accurately. So it's possible for this line to have a negative slope. If we had curved the line that way, you can see the line, secant line would have been negative, so that can happen, right? So this is what's known as the average rate of change, and all this is the slope of the secant line, okay? So as this curve, because this graph is curved, if we pick two different values, we're going to get different lines. So if I picked 2 points here, I would get a completely different slope between those two values as between these two values, okay? So what the difference quotient does is the difference quotient takes the average rate of change, and it says, well, let's push these 2 points closer and closer and closer together. And eventually, if we get them close enough, oops, I can't draw today, right? Eventually, if we get them close enough, we're going to get a tangent line. So as delta x, right, goes to 0, the slope of the secant line will equal the slope of the tangent line. So if you just took that top point and just kept sliding it, like almost like busy beads, right? Just kept sliding it over and over and over and over. Eventually, the distance between the x distance between the 2 points gets so close that it's gonna, the slope of the line is gonna like curve up as it goes over, and you're gonna basically end up with a tangent line. And the difference quotient is what gives you that value. So here's what the difference quotient looks like. We say we'll take f of x plus h, subtract f of x, and divide by h, where h is essentially going to be the distance between the two x values that we have. And so as this value h goes to 0, you're really, what this is going to do for you in calculus is it's going to produce the slope of the tangent line. And that is a hugely important concept in Calc 1. So now that we kind of have the background, what we'll do Monday is we'll open up with some examples, and I'll show you how to deal with the algebra of working with these, because the algebra really gets people kind of in a pickle.